Well, hello and welcome to Solar Alberta's 2026 Solar Series. Today's session is called Energy Reimagined 2.0, the Basics of Microgrids. Please note that we have enabled closed captioning for this presentation. You can turn on the captioning in the toolbar at the bottom of your Zoom screen. My name is Stephanie Westland and I am the Education Lead at Solar Alberta. I'd like to take a minute to acknowledge that I am working day-to-day and hosting you today from the place traditionally called Mohkinstsis, also known as Calgary, Alberta. Calgary is located on the traditional territories of the people of the Treaty 7 region in southern Alberta. This includes the Blackfoot Confederacy, made up of the Siksika, Piikani, and Kainai First Nations, the Îethka Stoney Nakoda Nations, made up of the Chiniki, Bearspaw, and Goodstoney bands, and the Tsuut'ina First Nation. Calgary is also homeland to the historic Northwest Métis and to Métis Nation of Alberta Region 3. Today we'll be hearing from Dr. Andrea Kraj from Core Renewable Energy and Earl Badger from the University of Calgary. Following their presentations, there will be a question and answer period in which you can all participate. The entire session will wrap up in about an hour and a half. We are recording this session and will make the recording available on our website and YouTube channel. All of those who registered will receive an email with the video link once we have uploaded it. We will be using the Zoom Q&A for questions rather than the chat box, so please enter your questions in the Q&A section throughout the presentation. Also, please click the little thumbs up symbol to upvote any questions that you like. Before we move forward, we're going to do just a quick poll to get a sense of who we have joining us today. Please take a minute to answer the questions popping up on your screen now. And while some of you are doing that poll, please also take a minute to pop your name, land acknowledgement, and any contact information you are comfortable sharing in the chat so that others can look you up on LinkedIn or email you. Great, thank you so much. So it looks like we have really a mix of solar industry professionals or those in the related solar industry, as well as folks who are solar knowledgeable, solar curious, and then some of those others as well. So it's just great to have a little bit of information about the audience before we dive in. Now for a little bit about Solar Alberta. Solar Alberta is now in its 35th year of operation. We're a non-for-profit society dedicated to accelerating Alberta's transition to a just and sustainable future. We do so by advocating, educating, and serving as an industry and community hub for solar energy. Our membership is made up of approximately 200 individuals and 125 businesses. We also have more than 35,000 followers. We provide a number of services, including managing a solar directory through our website. In this way, we act as a bridge for installers, suppliers, and others solar-related businesses to connect with their customers and clients. That directory gets approximately 23,000 hits each year, and you can see a link to it in the chat. Throughout the year, we run free public solar series webinars like this one. You can find free archived videos of our previous webinars on our YouTube channel. And on Thursday, July 23rd, we'll be offering a free lunchtime webinar called Solar 101, Solar for Your Home or Business. If you've been thinking about going solar, this webinar is for you. Registration is free and can be completed through the link in the chat. While we already have a sponsor for that Solar 101 webinar, if you or your organization wants to work with us to educate the public about solar and solar-related technologies through sponsoring a future webinar, please reach out. For example, we have more than 180 people registered for today's webinar, which offers you an opportunity to introduce your company to new audiences. The email address for the sponsorship is being added to the chat. We also offer classes for those in the solar industry and those transitioning into it. We will be offering live online courses again starting this fall. We have finalized the dates for most of those classes, including our 4 technical courses, and are just working to confirm the dates for navigating Alberta's electricity grid. Please check back for registration details on our website soon. In the meantime, we do have on-demand courses and workshops available for purchase in the solar training videos section of our website, including our on-demand solar training course bundle, where you can get 3 or 4 of our technical courses for the price of 3. The link for all of that on-demand training courses and workshops is being placed in the chat. In addition to providing education about solar, we advocate for it. We are currently rising up for renewables. We have free lawn signs available for pickup in 10 municipalities, and we offer free delivery in 8 municipalities around Alberta. We have recently updated the template letters for you to use on our website, asking the Government of Alberta to eliminate discriminatory rules and regulations that they've established for renewable energy. You can click on the link in the chat to make a free sign order or to use our template letters today. And even if you've sent a letter in the past using one of those templates, please consider doing so again with the new template. Also, Solar Alberta's second annual golf tournament fundraiser is coming up on June 8th, 2026 at the Inglewood Golf Club in Calgary. This is a great networking opportunity for those in the solar industry and those moving into it. New for this year, even if you're not a golfer, you can skip the greens and join us for a meal at the golf club. We still have a bit of room for a few more teams, as well as those who want to join for the meal, so we've extended the deadline to register until this Friday at noon. We also still have a bit of room for more prize sponsors for this event, so there are more details for registration and prize sponsorships available in the chat. And next week, we're starting to accept donations for Solar Alberta's 2026 Summer Online Auction, which will run August through mid-September. And all funds raised through that will help us to achieve our goal of accelerating a just and sustainable energy future for Alberta. Solar Alberta will recognize all donors prominently on the online auction website, as well as in our social media through our newsletter and our annual report. If you'd like more information, please reach out to the email being added to the chat now. And if you're not already a Solar Alberta member, I do encourage you to join us. Individual memberships are only $35 and can be purchased at the link in the chat. If you're looking to support the work that we're doing at Solar Alberta in additional ways, please consider volunteering, donating, or sponsoring a future webinar. We were not able to get a sponsor for today's webinar, so if you're able, we would appreciate any donations that would help offset our costs for today. And now, without further ado, I'd love to introduce today's speakers. First, we'll be hearing from Andrea Kraj, who is the founder of Core Renewable Energy and also the research chair in sustainable construction at Red River College Polytechnic, where she advances applied research at the intersection of clean energy and the built environment. A Fulbright scholar, TEDx speaker, and professional engineer, she is a recognized leader in intelligent energy systems, microgrids, and smart grid technologies for smart cities. With a career spanning more than 20 years, Dr. Kraj has been at the forefront of designing and implementing resilient, decentralized energy systems that accelerate renewable integration and reduce dependence on fossil fuels. Her work has had a tangible impact in remote and underserved regions, including northern communities, First Nations, island nations, places where reliable and sustainable energy access is critical. Then we'll hear from Earl Badger, who is the Director of Energy and Utilities at the University of Calgary, where he leads the operation and development of a campus-scale district energy system integrating cooling, heating, and on-site power generation. His work focuses on optimizing complex energy infrastructure while advancing practical approaches to decarbonization, including cogeneration, solar, and emerging microgrid strategies. With more than 15 years of experience across public sector energy systems, Earl brings a combination of technical, financial, and strategic leadership. He has led utility procurement, regulatory engagement, and carbon compliance programs, and has developed the business cases and partnerships needed to move innovative energy projects from concept to implementation. I will now pass the mic over to Andrea to begin her presentation, and I look forward to chatting with all of you in the Q&A.
Thank you. I'm going to grab the screen share here. And how does that look?
Perfect.
All right. Thank you. Good afternoon, everyone, and thank you to Solar Alberta for the invitation. 2 years ago, I presented Energy Reimagined 1.0, where we focused on the fundamentals of microgrids and where they are, how they work, and where they are being deployed. But the energy landscape has shifted dramatically since then. Today, microgrids are no longer niche infrastructure projects. They're becoming foundational systems for resilience, digital infrastructure, electrification, and community continuity. So today's presentation will explore what has changed technologically, operationally, ecologically, economically, and philosophically, and why the future grid will look fundamentally different from the centralized systems we have inherited. So the traditional grid was designed around centralized generation, one-directional power flow, predictable demand, and relatively passive consumers. But today we are rapidly moving towards distributed generation, electric mobility, digital infrastructure, electrified heating, storage systems, and intelligent edge services and devices. The grid was not originally architected for millions of distributed energy resources communicating and responding in real time. So what we're witnessing is not simply an energy transition, it is a systems architecture transition. Energy systems are shifting from centralized control to distributed intelligence. In just 2 years, the conversation around microgrids has accelerated significantly. We've seen extreme weather events intensify, data center and AI electricity demand surge, EV adoption accelerate, battery costs continue to decline, and resilience move from a nice to have to a strategic necessity. The conversation has also shifted from decarbonization alone toward resilience, sovereignty, flexibility, and adaptive infrastructure. Microgrids are increasingly viewed as enabling platforms, not isolated backup systems. So let's go to the basics. Microgrids enable the transition to energy resilience. They're defined as a group of interconnected, local, and distributed energy resources that act as a single, controllable entity with respect to the grid. So these systems can connect and disconnect from the grid to operate in grid-connected or islanded mode. Microgrids can improve customer reliability and resilience to grid disturbances. Advanced microgrids also enable local power generation assets, including traditional generators, but also renewables and storage to keep the local grid running, even when the large grid experiences interruptions or for remote areas where there is no connection to the larger grid. Also, these advanced microgrids allow local assets to work together to save costs, extend duration of energy supplies, and produce revenue through market participation, effectively what I've called smart microgrids. So here's a great slide to show a simplified example of how a modern microgrid architecture operates as an integrated energy ecosystem. At the center, you have a microgrid controller, effectively the brain of the system. The controller continuously monitors generation, loads, storage, grid conditions, and operational priorities in real time. Connected to the system are multiple distributed energy resources, everything from solar PV, wind generation, battery energy storage, EV charging, and sometimes dispatchable generation or thermal systems. The utility grid still plays an important role, but the relationship becomes dynamic and bidirectional rather than purely dependent. What makes microgrids particularly powerful is the orchestration, and the system can optimize energy flow, prioritize critical loads, shave peaks, reduce demand charges, island during outages, and support resilience objectives automatically. So, for example, during a period of high solar production, the system may charge batteries or support EV infrastructure. And then during an outage, the microgrid can isolate itself from the utility grid and continue powering critical infrastructure independently. So increasingly, these systems are also integrating forecasting, predictive analytics, AI-driven dispatch, and real-time optimization. So while the schematic appears electrical in nature, modern microgrids are actually cyber-physical systems where energy infrastructure, software, communications, and operational intelligence all converge. But let's go back in time because history is really important to understand how we got here. Back in the 1800s, late 1800s, in 1882, Thomas Edison first had his power plant constructed, and it was known as the Manhattan Pearl Street Station. and it essentially acted as a microgrid since the centralized grid was not yet established. In 1886, Edison's firm had installed 58 direct current DC microgrids, and then went on with further development where it waned back and forth due to a host of other reasons, such as the adoption of alternating current and the prohibitive cost of grid infrastructure and the monopoly structure that took over most electrical power industry models. And yet, recent technological and legislative changes have led to the resurgence of microgrids. But we can't forget about Paul Lecour, who was also doing the work in Denmark at the same time. And I've actually been to the site. That's the picture on the top here. The wind turbine's no longer there, but the building still stands. And Paul was concerned about school and education and lighting and how important lighting is. Back then, lighting was provided by gas. And so he was really interested in obtaining hydrogen. And so what he did was he used the wind turbine on the top of his building there, and he produced electricity that then he used the process of electrolysis to produce the hydrogen for the gas. And he had batteries stored in the building in the back there. So these two pioneers were really leading the way on the early models of what microgrids were. Then I came along and I started working on this area and started to see how we could do better. And this was before we were calling them microgrids, really. What I started doing and developing was the integration of multiple types of renewables and storage, multiple types of storage, and putting it all together in a system, which originally I called a multiple renewable energy system because there was no real catchy name at that time for it. But it essentially is what today's modern microgrids are. A combination of various types of renewables, having a backup generation system, sometimes still a diesel genset in a lot of cases, and of course energy storage. And that could be through various types of energy storage systems. And of course the load that has to be served. And at the center of that system, which we called the brain, the operational control system. So at the most fundamental level, a microgrid is a localized energy system capable of operating either connected to the main utility grid or independently from it. Traditionally, most electricity systems were designed around that centralized generation model. Large power plants transmitting electricity long distances to consumers. A microgrid changes that architecture by bringing generation and storage and control closer to where energy is actually used. In a localized microgrid, you typically have local energy generation, local loads, and local controls, and increasingly local intelligence. So that might include the solar PV, the batteries, the EV charging, district energy, or backup generation integrated into a coordinated system. Now, one of the defining capabilities of a microgrid is islanding, and a lot of this work comes out of physical islands because of the needs that they have had. Islanding means the system can temporarily disconnect itself from the larger utility grid and continue operating independently. This is critically important during outages, extreme weather events, cyber disruptions, or grid instability. For example, if the main grid fails, the microgrid controller detects the disturbance, isolates the local system, and maintains power to critical infrastructure using local resources. And that critical infrastructure typically includes hospitals, campuses, remote communities, military bases, industrial facilities, or emergency shelters. The key idea is, instead of relying entirely on distant centralized infrastructure, localized and islanded microgrids create this regional resilience and operational autonomy. And as an energy system becomes more distributed, electrified, and digitally connected, this ability to localize and intelligently manage energy becomes increasingly valuable. And in many ways, microgrids represent that shift from a centralized dependency toward distributed resilience. And it's important to understand that there are many scales of microgrids. A pico is probably the smallest on the scale that I've ever heard of, and that is less than 1 kilowatt. Think of systems like when you go camping. Maybe it's a single solar panel and a small battery backup. Maybe it's just your backpack. That is a small system. It's called a pico microgrid. Nano is from 1 to 5 kilowatt. That could be something as a simple house, a residential 5 kilowatt system, or between 1 to 5. It could be another application. Maybe is something on a boat, could be 1 to 5 kilowatt. And then we get larger than 5 kilowatts. And that's when we start calling them microgrids. Because what is distinctly different about the microgrid is that it does have a larger storage system. It has some type of battery usually, or maybe compressed air, pumped hydro, so on. And of course, some type of mix of renewables. Now, not to forget, hybrid systems are also a part of this. But what changes the definition is that a typical hybrid system didn't typically have storage. What it had was a dispatchable source, such as a diesel genset, and one wind turbine. And this was that early beginning of a hybrid system. This term is still used today, but it's important to note that it is not considered necessarily a microgrid. A microgrid in itself really has to have that storage component and more than just say one or two things attached to it. Otherwise, it's just a hybrid system. So keep that in mind in your vocabulary. Now, what is different in microgrids 2.0? Well, they're fundamentally different than earlier implementations. As you've already heard me say, the first generation focused primarily on just islanding, backup generation, and local reliability. But today's systems are adaptive. They're adaptive ecosystems, and they integrate renewables, storage, thermal systems, forecasting, intelligent controls, mobility, which is becoming a huge part of it, and markets, and increasingly the AI-enabled optimization. So the future microgrid is not a static electrical system. It is a living operational platform. And we are moving from backup power toward energy intelligence. Traditional microgrids were reactive. Modern microgrids are predictive. Instead of simply responding to outages, they continuously optimize energy flows, costs, emissions, reliability, and operational priorities. The value proposition has evolved from keeping the lights on to continuously orchestrating resilient energy ecosystems. And when you think about what you could put into your microgrid, you really have a huge menu, what I like to call the menu or the spectrum of generation. You'll have solar options, everything from direct thermal and concentrated solar power. You also have wind. Wind could be onshore, it could be offshore, and we're seeing between that 5 kilowatt to 12 megawatt, which is the largest wind turbine, which is the 12 megawatts offshore, keep that in mind. There's a huge range of what is possible with wind. There are also smaller, like micro wind turbines as well, to keep in mind. Bioenergy has so many options as well as water. Water could be run of the river. It could be tidal in certain locations, wave, and small hydro. Large hydro is not typically considered renewable due to the environmental impacts that it has. Keep that in mind, but it is still on that renewable spectrum. And storage, there are many options that we're going to discuss right away across the storage spectrum. Okay, but why? Why can't we just use one thing? And the reason is, the problem can't be solved with just one renewable resource, because the problem with introducing one variable renewable resource is the fluctuation of its production. As you can see here, this is a 1-month snapshot of wind. And you can see there's always wind. People argue that there's no wind. No, there's always going to be some wind. The problem is, what is the cut in and cut out speed of the wind that works for that particular device, that wind turbine? So the wind speed has to be at a certain speed to cut in and actually start producing power, as well as if you have gusts or storms, that wind turbine has to be powered down so it doesn't damage the technology. So there's always wind. How does it fit in the zone? You can't necessarily rely on it to be consistent because of the inherent variability in it. And then we have solar. The same thing happens with solar. It can't be just solved with solar alone because there's a natural variability. As you can see here, day 1, 2, and 3, they're all a little different. Compiled together, you can see what that looks like, the change in the day, usually to clouds, to other things that might be happening. But the thing is that it's statistically representative so that the uncertainty is gone. And that's why we know solar can be reliable. And so when we start putting these different resources together, that's when we build the resiliency in the system, because the solution isn't just one. It's going to be the right combination of the right resources at the right place and time. And that's how you build a resilient system with storage. So speaking of storage, when we talk about energy storage in microgrids, it's important to understand that there is no one single best storage solution. Batteries are popular, but that's not the only one. And there are many types of batteries. Different storage technologies serve different purposes depending on the scale, the response time, the deployment duration, autonomy requirements, and operational objectives. So rather than thinking about storage as one technology, it's better to think about it as a spectrum of capabilities. At the shortest duration and fastest response end of the spectrum, we have technologies like supercapacitors. On the milliseconds, they're used primarily for power quality, voltage stabilization, frequency regulation, and smoothing transient fluctuations. They provide extremely fast response, but only for short durations. Moving further along the spectrum, we reach battery energy storage systems, which are becoming central to modern microgrids. Lithium-ion systems are common today, and they provide that short to medium duration outage. Renewable smoothing, peak shaving, backup power, energy arbitrage, and grid support services. And they operate for minutes, hours, and sometimes daily cycling applications. As we continue scaling toward longer autonomy requirements, we begin considering flow batteries, thermal storage, hydrogen, compressed air, pump hydro, or hybrid systems. These longer duration systems become increasingly important when resilience is the primary objective. For example, a campus microgrid designed for peak shaving may only require several hours of storage, but a remote northern community attempting to reduce diesel dependence with prolonged outages or seasonal variability may require even weeks of energy autonomy. So the storage question is always contextual. What are we optimizing for? Economics, resilience, emissions reductions, reliability, operational flexibility, black start capability, etc. And most importantly, storage is not only electrical. Thermal storage is becoming increasingly important in integrated energy systems, especially for district energy, building loads, and industrial heat applications. So in the future, many advanced microgrids will likely use layered storage architectures, where multiple storage technologies to operate together. There's going to be a fast response system for stability, batteries for operational balancing, and long duration systems for resilience and seasonal flexibility. So ultimately, energy storage is not simply about storing electricity, it's about managing time, flexibility, risk, and system resilience. But despite all the digital intelligence being added to these systems, the underlying physics still matter deeply. Renewables are variable, storage has limits, and loads fluctuate. So thermal systems also respond slowly. Power quality will matter. No matter the amount of software it eliminates, there's still going to be some intermittency, harmonics, inertia, dispatch constraints, or grid balancing requirements. So one of the biggest misconceptions in energy transition conversations is assuming that the digitization replaces physics. It doesn't. The future grid must combine advanced intelligence with rigorous engineering. And resilience is no longer just electrical. We now need layered resilience across energy, thermal, communications, mobility, water, food systems, etc. Microgrids are increasingly becoming community continuity infrastructure. And in many future deployments, microgrids will support emergency shelters, telecom, water treatment, district energy, transportation, all simultaneously. And that changes how we think about infrastructure entirely. And here we can see how the evolution towards interconnected community resilience comes together. Traditionally, when the grid failed, everything failed together. But in future architectures, critical nodes remain operational. And that comes back to that islanding concept, where our hospitals, our telecom, our critical infrastructure can remain functional. And resilience becomes distributed rather than centralized. And that fundamentally changes recovery capability during disruption. But one of the most important opportunities in this transition is supporting Indigenous and remote community energy sovereignty. The strongest systems are designed with communities, not imposed onto them. And energy systems in remote regions must reflect local priorities, environmental realities, cultural relationships, and long-term community ownership. Microgrids can support diesel replacement, local economic development, energy independence, resilience, and improved quality of life. But success will depend on reciprocity, collaboration, and co-design. There are many benefits as well as challenges of microgrids, from resilience and autonomy and safety, the affordability and performance outcomes, and optimized generation and the willingness to be deployed. But there are still challenges in the complexity, in financing, in the value being understood, the training and education and policy and support mechanisms. So speaking of those policy and support mechanisms, there are regulatory issues across Canada, being that every province has its own jurisdiction over its energy, yet there are still federal and provincial goals that must be achieved. And one of the defining characteristics of Canada's energy landscape is that there is no single Canadian electrical system. Instead, Canada is a patchwork of very different provincial and territorial regulatory structures, resource mixes, market models, and renewable energy opportunities. And some provinces operate large hydro-dominated systems, others rely on fossil fuels, while others have rapid renewables deployment and distributed energy resources. So we see major differences in utility structures, deregulation, net metering frameworks, interconnection requirements, permitting, carbon policy, and the support for distributed generation. Alberta operates one of the most deregulated electricity markets in North America, which creates both opportunities and complexities for renewable integration and microgrids, whereas provinces like Manitoba and British Columbia are dominated by vertically integrated hydro utilities, which creates a very different operational and economic environment, where remote northern communities face entirely different reality, again, often dependent on the diesel generation and limited transmission infrastructure and very high energy costs. So this diversity creates both challenges and opportunities, and it means this energy transition strategy cannot simply be copied from one province to another. There's technical solutions and business models and regulatory pathways that must all be adapted to local conditions. And at the same time, this diversity makes Canada an incredibly valuable living laboratory for energy innovation. Now, what does that look like in regulatory diversity? Well, across Canada, it is completely different. And this is why regulation is one of the most important factors shaping renewable energy and microgrid deployment. Primarily, it is led by provincial jurisdiction. And so, as I mentioned, market structure, utility model, all these things are different. And so as a result, the same microgrid or renewable project can look very different depending on where it is located economically and operationally, depending how it is deployed. So keeping that in mind. Now let's look at some applications. We have the Zeni-Gwitchin First Nations microgrid in BC. The project includes integration of 250 kilowatts of PV, a 1 megawatt hour lithium ion energy storage system with 3 95 kilowatt diesel gensets to support 2 banks of load in the central and west communities. And as of November 22, it's been able to turn on and it is supporting the communities, which is a great story. We also have an example in an Arctic mining community in Quebec where one of the wind turbines was erected and then the second one of 3 megawatts was coupled with a bidirectional lithium ion battery. And it is about a 40% renewable energy ratio, which is the penetration of renewables with storage energy and control systems that play a critical role in managing the variations due to the wind fluctuations, as discussed, as well as preserving grid failure in the event of a turbine malfunction. And one of the other things we're going to get to right away, and Earl's going to come up and talk about what they're doing at UU Calgary, is a campus microgrid. And campus environments are fantastic because it's actually one of the strongest applications for microgrid deployment because campuses already behave like small cities. They contain the multiple buildings, diverse load profiles, thermal systems, mobility infrastructure, research facilities, communication systems, and critical operations. And when they're all concentrated within a manageable geographic footprint, it makes it an ideal living laboratory for integrated energy systems, combining solar, battery, district energy, EV charging, backup generation, intelligent controls, etc. And so we're going to hear a little bit more about this shortly. But campuses are also increasingly important as demonstration and training environments. They allow students, researchers, and industry to really work together and find the best solutions. So they represent that bridge between theory and deployment. And as electrification accelerates, campuses may increasingly function as prototypes for the future distributed energy systems we will eventually see at community and city scale. Now, the big question we're all hearing about probably daily is data centers. I'd be remiss to not talk about this at all, but AI and digital infrastructure are rapidly reshaping global energy demand. Partially as we electrify our grid, we also need the control systems and the data to manage those systems. So they go hand in hand. And data centers are becoming some of the fastest growing electric loads in the world. That creates major challenge, but also major opportunity. Future data centers will increasingly require local generation, battery systems, predictive controls, and real-time optimizations. This is really important when we start to see renewable microgrids and sustainability being combined with the data center model so that they can be more sustainable and better for the environment. So AI is not only driving electricity demand, it is also becoming a tool for optimizing energy systems themselves. So keep that in mind. And the future digital economy will depend on resilient, localized power systems. Now, this is really important, is that infrastructure has often been extractive and taking resources, consuming land, consuming energy, and generating waste. But future infrastructure must become regenerative. Infrastructure should restore ecosystems, support communities, and enhance resilience, and create that reciprocal value that is so important to our communities and to us in our livelihoods. Infrastructure must return more than it takes. And this is simply not a technology challenge, it's a philosophical and systems designed challenge. So the future energy ecosystem is becoming increasingly interconnected and autonomous. And what we are moving towards is V2G, which is vehicle to grid systems, transactive energy, virtual power plants, adaptive grids, AI agents, and self-healing infrastructure. And the future grid may no longer be a single entity. Instead, it becomes a network of intelligent systems continuously coordinating in real time. And the pace of change is accelerating dramatically. And that future grid will not be one grid. It will be interconnected, intelligent, decentralized, resilient, and adaptive. The challenge before us is not simply deploying more technology. It's in designing systems that are technically sound, socially resilient, environmentally regenerative, and operationally intelligent. And that transition will require collaboration across engineering, policy, utilities, communities, research, and industry. And importantly, we're still early. Thank you for your time and attention. I appreciate the opportunity to share these ideas with you today. And I'd be happy to continue the discussion and take any questions after Earl's presentation. So I'm going to pass the mic now to Earl.
Okay, thank you very much, Andrea, for that very detailed update on the current state of microgrids. And also thank you to Stephanie and Solar Alberta for the introduction. Just getting my share screen going here. So a couple of things from Andrea's presentation there that is really important, and it's been part of the university's journey. You know, we didn't initially set out to build a microgrid. In fact, as she mentioned, microgrids wasn't even a terminology that was used back in, you know, the early aughts when the university here got started. But it's been really helpful for us to adopt that perspective as we re-examine our infrastructure and start to build plans around how we're going to expand it and manage it going forward. So I think no matter where you may be on your journey, I think it's important to start adopting that outlook. And as a campus, we do exercise one of the main advantages of using this as a learning lab. So we do sponsor and support quite a few tours of our plant, both on campus groups and off-campus groups. So I'm just going to give a quick outline of our system that we have here. And, you know, following Andrea's description, you could probably surmise that it's not really a microgrid. It might be considered a hybrid in that current definition, mainly because we don't have any storage, although that is on our roadmap. So just a bit of background. We do have a district energy system at the university here. This is our main plant to give you a sense of scale for the systems that we have. And it has sort of three key components. One is a natural gas boiler plant that provides a lot of the heating load, a chiller plant that provides chilled water for the campus, And then the topic of this discussion, which is our electrical microgrid, which is composed of a thermal generation unit, which is the backbone, and then a bit of solar scattered around, and quite an extensive high voltage distribution network. And all told, we provide energy to 55 buildings here on campus with over 9 million square feet of occupied space. So it's quite a large system. This is a top view of our plant. The building in white there, you can see the top rectangle is our turbine hall. That's got the main exhaust stack on the left there. And then in the middle is the heating plant, the boiler plant, and then at the bottom is the chiller plant. It's kind of zooming in on the microgrid component. The backbone of it, as I mentioned, is a thermal generation. That's a carbon-based system. And really, for us, with the size of our load and the density of our campus, there's a limited opportunity for renewables on campus. So we rely on this natural gas-fired system. Although we do have 6 solar PV arrays scattered around, sizes up to about 220 kilowatt. And we have some variations in the operating voltages. We have our distribution network, which comes out of our microgrid, is primarily at 13.2 kilovolt. And then in individual buildings, that's a step down to around the 600 volt range. In order to complete the distribution, we have altogether 19 kilometers of high voltage cable with numerous splices, and this is all contained in a tunnel system on campus that covers about 7 kilometers. And then within that, distributed again around campus, we have 6 metered connections to the electrical grid. And right now, one of them which is connected to our thermal generation unit, it's set up for unlimited supply and export. So that's our main export of excess power. This is a quick schematic of what our cogen unit looks like. You can kind of start in the center of the picture there where it shows that gas turbine. And then just to the left is where the combustion air comes in. The combustor is there, and then the hot gas exits to the right, driving the turbine. And then that shaft of that turbine is connected to the left. It runs right through into the generator where we produce the electrical power. The hot gas then exits to the right, and we have this bypass chamber where we can, if we don't have sufficient thermal load, we can vent some of the heat directly out the stack there. Otherwise, it carries on to the right, and if our thermal load exceeds what we are expected to recover from the heat recovery boiler, we can add supplemental heat there. And then lastly, it flows into this water tube heat recovery boiler where we generate high temp hot water at roughly 400 degrees F or 300 C. And then that red stack is where the exhaust gas finally exits the system. This gives you a scale again of the size of that unit. Over on the right, that blank panel, that's where the generator sits. And then to the left, you can see the turbine and the combustor. And this is just a bit closer look at that part of it. The worker there is working right on the wall that divides the turbine from the generator on the right, and then you can see the combustion air coming in on the left, and then the combustor and the turbine itself on the far left there. And this is the control room for the plant. We use an ABB DCS system to coordinate all the equipment here. As far as our solar systems go, as I mentioned, we don't have a lot of area to put panels on like our buildings. So it's quite limited what we have, but it is a bit interesting in the range of different systems we have there. We have one system that was installed in 2007 on the Child Development Center, which at the time was actually the largest system installed in Calgary, and it is kind of unique in that a lot of the array is also used as window shading to prevent overheating in the summer. But we have a variety of other configurations, rooftop, of course, but also a large vertical array, some ground mount systems, and we've even got some building integrated photovoltaics on some of our buildings. And we don't have a fixed plan to roll out additional renewables on campus, but every major building renovation or build looks at the possibility of adding new resources there. This is a couple of the unique examples. The one on the left is that vertical array, which was quite an interesting solution. That building needed to get its exterior cladding redone, and it was almost like a zero cost option to put solar panels up there as the exterior cladding instead of what would conventionally be used. And the one on the right shows a building integrated photovoltaic system where the windows actually have solar panels embedded in them. As for our distribution network, and apologies for the blurriness here, but you can kind of get the idea. Each of the kind of green squares are different buildings on campus, and in the lower left-hand corner, that little red square is our district energy plant. And then the blue and red lines are distribution lines that are chilled water and hot water that run in tunnels around campus. And to give you an idea of what those tunnels look like, here's a quick picture of one. And the pipe rack on the left contains the high temp hot water at the top, the supply, return, chilled water, and then in the front is domestic water that's distributed. But one of the interesting things here is on the ceiling, you can see those two red curving lines. That's our high voltage distribution cable that's coming from our generator, going out to various buildings where it gets converted down to 600 volts. And this is a typical switchgear lineup that you'd find in a building or another node. And each of these panels open up, and there's either breakers or switches or interconnections of one sort or another. And we have like dozens of these all around campus. Give me an idea of the scale of our demand and why it's so hard to meet it with renewables. 125,000 megawatt hours a year. And right now, like cogen is producing a good chunk of that, almost 100,000. And then the balance we end up purchasing from the electrical grid. And finally, as we're looking at going forward, these are some of the things that we're working on as we evolve our microgrid. We're adding more distribution cabling on campus so that we could eventually consume all the power that we generate from our cogen unit behind the meter, if desired. Adding, of course, additional solar arrays, and we're looking at battery storage options. Another one we're looking at is an organic Rankine cycle generator, which uses a low-grade heat source to generate electricity. It's you can kind of think of it as a heat pump running backwards. So in a heat pump, you put in electricity and you get out heat. With an ORC generator, you put in heat and get out electricity. So we have some times of the year when we don't have enough base thermal load from our heating requirements. We have to vent potential heat out into the atmosphere, and this ORC would be like a dispatchable thermal load that we could connect and disconnect as required. And we're, of course, upgrading our energy management information system and also looking at more automated and different control logic to optimize when we're generating and when we're exporting, and how to change the configuration of the grid without so much manual switching orders and manual breaker switching and that sort of thing. So that is everything I had, and I will stop sharing and turn it back to Stephanie for question answer.
Super, thanks. And Andrea, yeah, if you can join us too, that would be amazing. So our Q&A is already very active. So I just want to remind you that you can put your questions in the Q&A rather than in the chat. And we may not be able to get to all of the questions. And so it's really helpful if you can use that thumbs up symbol. And I use that to ask the order of the questions. So I ask the questions with the most upvotes first. So let's dive in here. Joe is asking about whether microgrids always require a microgrid controller. He's wondering about whether these types of controllers make systems vulnerable to loss of communications, and whether there's a way to design them to minimize the need for controllers or communications.
I guess that one's for me. Yeah, so there is always going to be some type of control because you have various types of assets. Now, the complexity of a controller for a home microgrid is far less than that for a large utility scale microgrid, which has many more assets, possibly larger, obviously larger in scale, but not necessarily more. It might just have a larger solar grid, right? But along that part of it, you'll have many different arrays. You'll have some that are producing, some that are not, perhaps. There's different things going on just within that. So there's always some level of control that has to happen, and there's going to be different types of controllers. So keep that in mind. But yes, there will always be something controlling the system.
Earl, anything to add?
Yeah, no, I would agree with that, but it doesn't have to be a one controller, master controller doing everything. Like our system is a good example that even though it's very complex and we have a industrial scale DCS system running our plant, there's still a lot of manual work to reconfigure our grid on particular situations that our electricians go out and close breakers and open switches, and so it can always be a bit of a blend as well.
Mm-hmm. Yeah.
Thank you. Again, Joe asking the popular questions. Beyond campuses, what other sites would make excellent candidates for microgrids?
Is that one for me too, I guess? Okay, so there's everywhere. I mean, like, it could be literally your house. Let's start there. One of the projects we worked on was for the city of Winnipeg's bus depot. They came to us and said, we need more power and it's too expensive to connect to the municipal grid. What do we do? And I'm like, you need a microgrid. That was the first introduction as to even the language they didn't know what to use for describing this. And what it came down to was about just over 1 megawatt of solar panels and I think it was like 4 megawatt hours of batteries and obviously some control systems for like just one part of their garage, and they have a future expansion as well. So like e-fleet mobilization is a great application, and there's cities all over the world that are doing that now. I mean, if you're looking at remote cottage systems, like fishing lodges, remote communities, those are just like very straightforward, as I already mentioned. Islands, we've worked with islands at the utility scale, 21 megawatts, all the way to, like I said, small homes. So really anything along that spectrum that the purpose is you need to have resilience and you need to have some sort of control over your energy, and you want it to be localized. And that sometimes is driven by resilience from just having your lights on. Sometimes it's by cost. So anywhere along that spectrum, I would say.
Prowal, I'm pronouncing that name correctly, was really interested in the vertical array of solar panels that you have on the social sciences building there, Earl. Now, I'm not sure if any of you can answer this question. Is this concept being used in current multi-storied building construction practices in Alberta? So I don't know, Earl, if you know if it's been done anywhere else, or were you the first building to do it?
No, vertical arrays on a wall of a building are definitely a viable option in a lot of places, particularly as the cost of solar panels has come down so much that, obviously if you want to get maximum production from your array, you want to have it, facing due south and oriented at just the right angle. But you can compromise that to quite a significant degree and make up for it just by adding more panels. So if your installation cost per panel goes down, you can just increase the number of panels. And in a particular, like in Alberta, you have a lot of reflection off the ground. Like even if you're somewhere where you have a snow cover, you're going to get a lot of production out of that system in the winter. And the sun is very low on the horizon, so it actually kind of is optimizing for winter production. So I think it's always a good option to examine if you're in a situation where you want to add a solar array, but you don't have a lot of roof space. It's certainly worth examining.
Yeah, for sure. There is a house in the community over from mine that does have a vertical array. I've always wondered a little bit about it, but haven't knocked on their door.
Uh-huh.
But anyways, there's a few people popping some information in the chat, so thanks very much. Joe is again wondering about whether you can expand on the value that a microgrid can generate. Are there changes to a market that could unlock new value for either communities or building owners or occupants?
I could maybe jump in here for a little bit to from the university's perspective. The value of our on-site generation, for one, definitely resiliency. We're in the event the university has been designated as an emergency response sort of headquarter in the city of Calgary's emergency response plan. So we could have any number of emergency medical or fire or safety people moved or stationed here, or people who have been evacuated from different communities come to stay here. And for us to be able to switch to island mode and keep that running into those emergency situations is a real valuable asset to the whole community. And also on the cost side, we can generate our power, it's sort of a mix of power generated and power bought, but our overall power costs over the year are much lower than it would be if we were just buying all our power. And also, this is kind of not quite as monetizable anymore, but when they first put in our cogen plant, we had about a 30% reduction in our Scope 1 carbon emissions. And so that carries forward as a significant environmental benefit and meets some of the university's goals around sustainability, but it's a little harder to monetize nowadays. But yeah.
I was going to jump in too, is that one of the things when you're evaluating the cost of something, the metric you really need to look at is called the levelized cost of energy. That energy does have an electrical and a thermal component, so keep that in mind. But generally what we need to look at is what is that price? And I mean, if you're just putting in one, and this comes from research, my scientific background and everything. So if you were to put in just one device and maybe oversize the storage, it's going to cost you very different than if you find the right amount of the right size generation with the right size storage, so you're not overpricing on what might still be very expensive. Storage is still expensive compared to distributed assets such as solar and wind and so on. You need to size it appropriately to get the right cost. So keeping that in mind, what we've seen, even in Manitoba where I'm located, and this was a couple years ago now when we had a solar rebate kind of takeoff, we saw that the large scale wind solar farms were just as competitive, if not lower than the cost of what the hydro utility was advocating for on price. But the issue there, is really user knowledge and education and willingness to take on that risk, because it still seems risky, right? But when you look at the levelized cost of electricity and you see like, wow, this is my price today and this is my fixed price over the lifetime of my asset, 25, 30 plus years now with some of these technologies, it's a no-brainer to invest in it today and own it and pay it off and lock in that price, rather than what we're seeing with increased prices increasing everywhere, especially with the fuel crisis. So that's something to keep in mind as you transition to renewables. It's something that you can look at that price and compare today and lock it in as a power asset.
Right. Thank you both. Just a warning, my internet is giving me that message that is unstable and it just knocked me out of the webinar for a minute. So if that happens again, just jump to the next question in the Q&A yourselves. Hopefully it won't do it again. Joe is wondering about where to find guidance for the design of microgrid applications.
Ask me. Send me an email. More than like, I mean, it's one of those things where there's many people who you probably reach out to. I don't know how many specialists exactly are out there. This is my jam. But yeah, if you have any questions, feel free to reach out, and maybe through Solar Alberta, you have some context too on what's available. But that's something we can definitely look into and support and help on where the more information could come from.
Right. Yeah, I'm just popping onto our website right now to see if we have a microgrids category in our directory. If we don't, maybe we should. So that would be good.
One not to advertise for anyone in particular, but one organization that's helped us quite a bit, because they're quite generous with presentations and have a full suite of solutions for industrial type of microgrids, is Schneider Electric. And so they have a whole product line around this, and there's a lot of material available through them.
Okay. Thank you. An anonymous attendee is asking Earl about the campus's ice rink, and is the university considering using any kind of heat recovery system to provide low carbon heating as part of the DE network? He said I might have missed that when you reviewed your portfolio.
Yeah, no problem. The Olympic Oval is actually part of our district energy network on campus. So we do provide heating from our heat recovery boiler and chilled water from an actually interesting system that we use. I didn't really touch on it too much here, but we pipe water from the Bow River up to campus and use that to provide free cooling. So all winter we aren't required to run our chillers. The Olympic Oval is connected to all of those systems. So.
Okay. Thank you. Stephen is asking, even though we've been talking heat, I noticed that geothermal or enhanced geothermal didn't show up. Is that because of geographical constraints, or just that the technology is considered at an early stage?
No, I would say geothermal is actually conventional already. It's just there are some places where it is more efficient and better to use. Absolutely. There are still costs associated to how it is deployed. There are constraints, land sometimes, location, etc. But I just didn't put it in as an example, but it's definitely on the spectrum of very valid applications. Earl, did you want to add?
Yeah, we just actually completed quite a detailed feasibility study to try and see if our campus could reach net zero by 2050, like a lot of organizations. And, if we take away, the big one is how do we provide heating, like on a campus like this with such a high density of buildings. And so to try and substitute a carbon-based system with some kind of renewable system, your large scale, heat pump and earth energy systems are really like the only option that's out there for you. But when you look at like how dense our heating demand is, like I think it would ended up being 1,500 well bores that we needed to have that were like over 700 feet deep. And the cost was in like the hundreds of millions of dollars. So it becomes a real challenge. It is a definitely viable opportunity, and it particularly, again, as Andrea mentioned, it depends on your particular situation. If you don't have a lot of space available and you have a very high load, it's going to be a real challenge. And if you look at going deeper, like we looked at going to like a deep geothermal with water temperatures that would be sufficient to generate electricity, because if we remove our cogen unit, we're not only losing our produced heat, but also our produced electricity. In Alberta, with our geology, that means drilling down, 4 kilometers, in that range. And you have to pass through like a sour gas layer. So now you're talking about drilling through sour gas, and in like an urban location, it's virtually impossible to get that permitted. So yeah, there's a lot of challenges. So it's an option, but as you scale up, I think it becomes harder and harder to implement.
Wow, that does sound for sure complicated. I hadn't really thought about what are the differences in geography and how that would affect the implementation of geothermal. Jacob is wondering, for you, Earl, to replace the amount of generation that the U of C purchases from the grid, what percentage of overbuild would you aim for if you were to replace the amount of energy with campus solar panels?
Yeah, I kind of did a back of the napkin on that, and it would be something like 250,000 panels we would need.
Wow.
Yeah, again, and that's just to meet like the overall annual demand. That's not to meet like our peak demand, and so you would have to combine that obviously with something to cover you for periods when you don't have that intermittent resource producing. So yeah.
Right. I think that would be maybe not possible to be totally with solar. I guess that's why you, as Andrea was talking, right?
Yeah, it's really not a practical option for a campus that's as dense as ours, and like our building roofs just have very little room on them by the time you eliminate, the border and all the other equipment that's already on the roof and access paths, and yeah, there just isn't that much there.
Right. Andrea, did you want to say something?
No, it just comes down to space. Exactly what Earl was saying is that what space do you have, but then how can you get creative? Because one of the interesting movements, even, it's very popular in Europe right now, is agro photovoltaics. And there's sort of different ways of doing this. Is similar to the carport model where you can put it over, land rather than cars, but also the vertical face on fencing is very popular as well. Just depends where though. And of course, latitude is so important where you are. So what might work in a certain latitude in Europe may not work where you are. That's something to keep in mind. Hence vertical versus, angled panel placements.
Right. Okay. Next question, because there's still a lot to get through. Joe is wondering, are there examples of innovation in the use of thermal storage that you think are exciting? Feel free, both of you, to jump in if you have an opinion.
There probably are. I'm just having what am I thinking? I'm trying to think on the spot. What would that be? Earl, do you have anything that comes to mind?
Well, one of the things that again, as part of our feasibility study, we looked at thermal storage in the ground, and by piping excess heat down into the ground, like over the summer, and then extracting it over the winter. So a long-term thermal energy storage, and it's actually interesting how effective that is. Like you think piping a hot heat down into the ground, like is it still going to be there in 6 months when you go back to extract it? And it's actually quite surprising how insulative the ground is and how little that heat actually dissipates while it's down there. And if you're combining like heating and cooling, like how do you recharge that ground storage and extract it? So I think that's obviously it has been an active area for quite a while, but I think there's some good opportunities there.
Part of it, I don't know that it would be innovative. It seems like it's almost ancient knowledge in some ways. Is how we are building, like working in the built environment, and how we are not only like leveraging, like you're thinking about innovation, new stuff, molten salt batteries, and so on. But like part of the heating is actually building. Excuse me, is how we build our buildings and what sort of heat sinks we adapt and put into them, and where can we use perhaps cement to hold heat. Throughout the day, as we've seen in many indigenous cultures, even in, I would say in the south, like of North America, right, in the southern parts, the deserts, how they're holding their heat in their buildings traditionally. So I think there's part of it is looking back and learning and relearning that tradition, and part of it is, okay, what is new and innovative, and what can we do moving forward? So thinking along both those lines.
Right. Some creative thinking for sure. Okay, Julie has a totally different, we're going to a totally different topic, but well, microgrid still. So she says, I have solar panels, electric oven, and induction hob, heat pump and EV, and upgraded my panel, and have a controller that automatically switches from charging the EV to reduce the load. I would like to add more solar panels and battery storage. Do I need to get a microgrid designed first?
I would think you'd probably want to get things aggregated first. Definitely talk to a specialist, or get some more information on that, because you do have a lot of assets that I'm not quite sure if they're all working in sync, or how you have them working, but it seems that they're probably working together to an extent. But if you need more, how much more of solar, and what size battery, like all of that would be really important to have assessed. So you really have a synchronized, holistic system, because you've done a phenomenal job to integrate so many aspects of what would be like a microgrid. So it might be worthwhile to review it, but to what extent you actually have to go to will depend on how much more you want to expand and how complicated it is. And maybe it's not complicated; it might just be a simple add-on. And though, like, electricians are going to be critical as well to work with you on your existing system and your panel and your requirements, I would think.
For sure. Marty is asking, can you please comment on the adoption of solid state batteries in microgrids?
On the adoption. Yeah, I think, there's a place, where exactly yet to be determined. How, I would never say no. I mean, there's always an option. I think it's sort of, I don't know if it's up and coming. It's sort of maybe on the fringe is a better way to say it. It's not, it's known of, but I haven't really heard too much about that being conventional yet, I would say. So definitely possible, still working through it.
Okay, Khalil, a giga project with storage gigawatt hours could help reduce dependence on the grid. Such projects are now expanding in China and the Middle East. Why not go through this path in Alberta? I don't know if either of you have a comment on that.
See, I'm not in Alberta, but I can tell you that this is a policy issue, and we know what the situation is in Alberta. But I think it comes back to the financing of it, the policy of it, what the other players in the market how would they be impacted. I think it's far more complex at that level. And the question is, gigawatts, are they needed in Alberta? I'm not sure. I haven't checked right now, but that's something that would have to be considered. What scale?
Okay. Gordon is giving you some advice, Earl, saying that meeting U of C's campus annual energy requirement would be easy. Just purchase the energy from a rural solar PV farm. Simple. So I don't know if that's something you've considered at all, but you're welcome to weigh in or not.
Yeah, we of course have been, I've been a member of the Business Renewables Center for many years and have looked at, the evolution of power purchase agreements and where they've, delivered value and not delivered value. And, in our particular situation, it just hasn't become a priority to really pursue that. As a public entity, the mandate to manage, our financial resources, very carefully is kind of paramount, and everything needs to be balanced against like our core function as a university. And so the main objective around our utility procurement is cost management is number one, and resiliency and all that. It forms a little bit, and unfortunately, sustainability requirements fall quite low. So if there's an additional cost associated with a strategy like that, it's really hard to prioritize that against all we're working against. But
Fair point. I think that we're all working against costs right now in a lot of ways. Gordon, these are some questions that came in at the beginning. So Gordon is wondering about why is the larger grid still needed if we have microgrids? And why are microgrids not completely separate from the big grid?
Okay, so why is the larger grid needed? Infrastructure already exists. It's been invested in. Why would we throw it out, right? As we upgrade, obviously parts have to be replaced. Things have to be continuously done, like upgraded to last. So there's sort of a refresh part, which allows microgrids to tie in nicely anyways. For example, I gave the example of the bus fleet part where it was in the city. It could have been connected to the grid, but the grid didn't have the capacity. And then now the financial sense was not there. So in these situations, it makes sense to put in a microgrid, even though there might be grid around you. Now, why do we still need to connect or disconnect? It's a choice. Sometimes, like in Earl's situation with his microgrid, doesn't have enough power. So the best thing, use the existing grid. It's essentially like a storage reserve of energy. So you might as well connect and disconnect. There's also jurisdictions that allow to sell your power, excess power, as a prosumer. You're a producer, not only a consumer of power. So you can have a business model off of that. Part of you is a consumer and part of you is a prosumer. Some jurisdictions just allow you to be a prosumer. Like say you have a large wind farm and you're just supplying the grid. You're not even consuming, you're just a producer of energy, right? The same model can work when you're kind of wearing both hats at different times. And so why do we still need microgrids? Well, I think this is where we build in resilience. So if the main grid does go down because one, it's aging, or two, there's been a natural disaster or something else, maybe it's overloaded, congestion, so on, you've got a microgrid node that can then help power that localized area, which brings resiliency. And just imagine, like I showed the graphic, multiple nodes all over. That is the vision of the future grid, because you may have a main grid as a backbone, but you can have multiple nodes of microgrids that help to provide that resiliency. So I hope that helps to answer.
Did you want to add anything, Earl? Or?
yeah, no, that's a really good summary. I mean, for the university, we do export excess power. We want to run our cogen plant 24/7, and obviously our demand load goes up and down. And when it's down, like at night, and we have excess power, so we utilize the grid, as you said, a big storage element to export that power, and we get paid for it. But also, like your microgrid is not 100% reliable, but your users demand 100% literally reliability. And so there are times where we have to take our cogen unit down for maintenance, and just preventative maintenance, not like unplanned failures. And under those situations, then you can ship the load back to the regular grid. So they really work well hand in hand. If you have that infrastructure already available, like it totally makes sense to maintain that connection.
I think Gordon had another terminology question for you, Andrea. This was from the beginning of your presentation, and he's saying that he's wondering if a house is fundamentally a microgrid, not a nanogrid, since house services are typically between 10 and 19 kilowatts.
Well, it depends. I've done a house that was 5 kilowatts and it was just solar. And so technically that's not a microgrid, but it's solar on the rooftop and it's providing the house with power. But that wouldn't necessarily be capable of operating on its own independently if there was no sun, right? So what a microgrid would be is dependent, one, that there's a scale part of it. The application doesn't really matter, I don't think. It's more of what we're looking at as the scale. So if you have a microgrid house, say you've got a 5 kilowatt, or maybe you have a 4 kilowatt, or less than, maybe let's go even lower. Let's go less than 1 kilowatt because you've put up one panel and you've got a little bit of a battery system. You would have a nano or a pico microgrid. It's just the scale, like pico and nano can go before the word microgrid. And then we just drop that when you're about 5 kilowatts and up, because those systems are the ones that are going to need larger scale storage and so on. So those have been what we typically designed around, but then we started having these smaller technologies go, but what about me? What about me? Am I a grid? Am I not? And so we just came up with language around, and this is not just me, I mean, this is the industry, with the language being pico and nano to gauge the size of those microgrids. So technically they're just smaller sets. And what's key about the microgrid is the storage component with the generation. And that's why I tried to show the difference where you have a hybrid system where a lot of people mix up, well, I have a hybrid system, it's a diesel genset and a wind turbine providing power. That's a hybrid power system. It's not necessarily a grid system. It's usually supplying maybe like one major load in a remote location. And so these systems, there's sometimes argued to be a grid, but as we move forward and we're designing more complex systems with multiple assets and multiple storage, multiple loads, possibly not just one chunk load, this is where we start to see that microgrid terminology come in. So I hope that helped to clarify it.
Thanks, Andrea. Earl, did you have anything to add?
No, I think for us, we struggle with the same thing. Like, are we a microgrid? Are we not? And based on all these little definitions, and I think the important thing is not necessarily to try and come up with like these criteria and these strict definitions and see whether you fit in there, but to adopt this kind of microgrid perspective as you're examining your infrastructure and how you want it to grow, and see what advantages of a microgrid you can bring to your system, whether it meets all the criteria as a microgrid or not. So it's more about a thought process and a perspective than anything.
Yeah, and just to add on that is that different jurisdictions are going to have different policy and some will have different code requirements. So the language, and just a comment back onto Gordon's comment about being able to handle 100 amps at 19 kilowatts and so on. Different jurisdictions and just the industry in general. This is just general language on microgrids, but you will have specific language within your jurisdiction in Alberta, perhaps related to codes and policy requirements. So just keep that in mind. That doesn't say it's not a microgrid or it is not there's a difference between that, and you in your local code will have to comply to whatever the jurisdiction requires.
Right. Fair point. Someone submitted a couple of questions. Most of the Q&A items right now, or maybe people want to have a look at them. There's a few plugs and such. But there were a few questions that got submitted in advance. And so one of them was asking, how does one determine the energy load required for any given application? Is there basic math for meeting that? Or like, is it really a matter of connecting with a professional like you, Andrea? Or
okay, so I could do a whole talk on energy vampires. That's like a whole sub talk. Okay. So, anything that is pulling electrons from you, you could look at your power bill and just be like, well, what's my annual consumption? And then like look at it across several years and you'll get a sense of how much power you need. Electrical. And of course, if you're using gas or if you have other thermal loads associated on your bill, it's going to be different per jurisdiction. Look at that. That's going to tell you how much you need. And then you definitely, before you get into designing and need permitting and you need engineering stamp drawings and all this, you would engage with a professional to get to that level of the professional level that you need to comply with permitting requirements to actually do an installation and so on. So the most basic thing you can do, look at your energy bill, see what you are consuming, and then go around your house and unplug all your vampire loads. I know I still deal with it all the time. We have so many things plugged in, but I think what's important is to also know, like, be that awareness around it. And I mean, you will see all the things that start consuming your power, and that will help you size it, because if you start unplugging all those things that you don't need, it's also going to change your demand requirements. So just that's the connection there.
Right. I think I remember reading an NRCan study that somewhere between 10 and 20% of the electricity we consume, like as Canadians, is vampire load.
Yes. Yeah.
So anything that's plugged in and on with a remote, with a that's on demand, sort of like a TV, yes, or anything that can be woken up.
Google, if you've got your little whatever Google thing.
Yeah.
It's always on listening.
Did you want to jump in, Earl?
Yeah, no, I don't really have anything to add to that. Yeah.
I imagine you have a lot of vampire load at the university.
Yeah, and we also employ a lot of designers and engineers and people to do very detailed calculations. So I wouldn't recommend anyone try and get a back of the napkin kind of quick and dirty. There are rules of thumb one can use, but as Andrea said, when you come to the point of actually wanting to build something, then yeah, you need someone with some detailed knowledge to do those calculations and prepare the documents for permitting and whatever else you need.
Okay. Another question that was submitted in advance was wondering about whether one could ever build a microgrid with that produces more energy than will be used. And is there ever an advantage to doing that?
Sure. Earl, you go. I'm talking too much. Go for it.
Yeah, well, you certainly can. And again, as Andrea mentioned, it's very jurisdictional dependent on where you are. Like here, if you're a private person putting on a solar array and you're going to take advantage of the microgen regulation, you're only allowed to generate by design 110% of your annual usage, because it's meant to just offset your usage. It's not meant to be a business case where you're now a power generator. So that restricts the size, but usually it's not. Like if you look like the annualized use, your generation may match your load, but at the variations through the day or the week or the month, you could easily be generating excess power that has to go somewhere. So it's definitely doable.
I would say, Earl, the other reason would be that you have a future forward look. Like you're thinking, okay, we're going to oversize our solar because we know it's more efficient now to build everything out and get it sorted. And then we're going to be expanding and putting in another building load or however else you might be, using it in the future coming time. So that sometimes things get over designed at the beginning, maybe because of the economics or the plan, and sometimes the plans shift. So there's also contingency and losses that you have to over design for just naturally. What's going to be important is you could over design, but you want to capture that storage. And this is one tagline I use all the time, and I promise the t-shirts are coming, but not all electrons are created equally. And what's really important is that what your solar electrons cost, what your wind will cost, what your battery ones will cost. Because one of the things that's happening right now, and this is something I read this week and then I realized I should really talk about this more, is that when we as personal, resident citizens put solar on our rooftops, the utility gets the benefit of using this solar if we are bidirectionally sending it back and forth without having to pay for that capital cost, right? And sometimes we are not reimbursed effectively. We get a subsidized low rate compared to what the utility is selling electricity for. So what does it make more sense to do? Well, keep your electrons. They cost you more money, so save them, store them, use them for yourself rather than sending them to the grid, because you know what? Your finance and your economics on it will make more sense that you actually use those electrons. Then the utility gets to use your CapEx, your capital expenditures on your home or wherever. So you really have to look at the economics and see what the investment is to put those electrons in a battery or a different type of storage, however you want to compress them. I don't know, whatever you want to do with your electrons. But think about that. because that's your value and that's your investment. And so, yeah, that's part of the ongoing conversation.
Amazing. Well, it's 1:30 and this has been a very active webinar. I really appreciate both you, Earl and Andrea, joining us and sharing your knowledge and insights. The chat has also been super active and I haven't really been able to keep an eye on what's going on there. So if I missed anything, my apologies, but I have seen some pop up, even one that said this is the best Solar Alberta webinar they've ever come to. So I really am grateful for everyone for attending and for both of you for giving your time to us today. And I hope we can do it again sometime.
My pleasure. Thank you, everybody.